Okay, so we have 2 hours, right? And then the first one in principle is tutorial. If you have any question, I could address it. If not, what I have thought is, because in the first day, well, in the first 2 days, we were through QCD and just to make it more or less clear how the things work, and then all of these commutators, right? I mean, just to construct chiral theories, at some point, it was essential to make use of these commutation relations that appear in QCD, right? So I thought that it could be a good idea that if we spend something like half an hour or something like that, just to see how to get these commutation relations, just to make it more digestible for you, that and then understand that you can understand that really QCD is predicting this thing, and that are the key relations that should be used later just to construct effective theories, because are based in C symmetries, in these symmetries, right? That it will cost something like half an hour or something like that. And then another thing I wanted to do in this first lecture is just to show and to discuss a little bit Gorston theorem, just to prove Gorston theorem for you, right? And then it will be just, then I will abandon totally QCD, and then in the next lecture I will start talking a little bit about the lambda 1405. And then Feng Kun has told me that you know everything about Riemann sheets, first Riemann sheets, second Riemann sheets, pole resonances, that will be better for me, right? Because then I could skip some of this stuff. So it's fine, or somebody else have any other suggestion? If not, I will try to discuss this. Okay, so I will start getting the vector current. Okay, I am going to focus on the vector current. You could do similarly the things for the axial current. The only thing is that in the case of the axial current, there will be an extra gamma 5, and then things will get extra minus signs. Because you know that in the Dirac algebra, when you have gamma 5, the gamma 5 anti-commutes with everything, right? So the next thing I need are the appropriate nodes that have a disaster. I am a bit disaster, but should be somewhere. Yeah, no. Yeah, okay. So let's do a vector transformation, right? Yeah, let's do a vector transformation. So you remember alpha is a color index, and then A is here is A is no flavor, right? You remember what A is? A goes from 1 to 8 in the case of SU3, right? Because TA are the Gelman matrices essentially, right? And it runs from 1 to 3 in the case of SU2, right? Because then TA will be the Pauli matrices, okay? So then we have a vector transformation. So then with QI is transformed into Q prime I, which is just e to the minus I. Okay, I'm going to put, yeah, okay, theta A, T A, and this is now a matrix in the SU3 space. It's a matrix in the SU3 space, right? Because well, in the SU3, because I am thinking in Gelman matrices, right? So here I am considering the 3 latest flavors, and then, okay, so it's a matrix. It's a matrix in the flavor space, and then you have Q set. Okay, to get the currents, you need to apply netted theorems, right? So then you need to see what is the variation of the field, okay? So then the thing is that you make this transformation infinitesimal. So you just take theta really, really small, infinitesimal, and then you just replace the exponential by 1 plus something, right? So then what we have here is q prime y is 1 minus I times theta a ta y set, q set. Okay, so then what is the variation of qi, qy? What is the variation of qy? Just because of the transformation is just this part, right? Right? And I don't care about the parameter, right? And then because, and I can choose different values of the parameters, so then all of them should lead to conserved currents, right? So now, next is, okay. Netter theorem, which is really, really important. And then for these internal transformations, right? So then the conserved current is just, the corresponding conserved current is just J mu equal the partial of the Lagrangian with respect the derivative of mu times the variation of the field, right? This is Netter's theorem. So we need to write the Lagrangian. Okay. Okay, so we need the Lagrangians. But writing the Lagrangian is very easy, right? Because the Lagrangian, the QCD Lagrangian contains what? Gluons that I don't care, because this transformation doesn't have, well, I haven't said explicitly, right? But these fields, they have color indices as well, right? These fields, they have color indices as well. Alpha is a color index. But then this matrix is the identity in the color space. So the color is not changed, right? So I am not going to worry about color any longer, right? So gluons, I don't care about gluons. I should care about what? The fermions, no? And how is the Lagrangian? How is the QCD Lagrangian for fermions? But with the mass, you should be careful a little bit, right? Because, well, it's going to be relevant, right? Because, okay, okay, minus m less, but that a matrix or something like that, right? A matrix or something like that, because we have yeah, it's a matrix or something like that. Okay, and then plus when we slash in another way around, right? And then let me see if we have a minus sign or not, or we don't have a minus sign, just to make it, So let me put it Okay, I am going to put the flavor index. I am going to put y here. I am going to put, just to have correctly the notation, I am going to put y here, and then here I have q y, right? And then I have yeah, it's with a minus. Then I have minus I over 2, and I have d mu q and everything bar y gamma mu q y, and then we include the master. Okay, right? So this covariant derivative d mu, this derivative covariant derivative d mu contains the normal derivative, the spatial derivative, plus gluons. Correct? So the only thing that we need is look at the conserved current that comes from Netter's theorem. You only need to take the partial with respect to the derivative of the field, right? So the only thing that really matters is this d mu here, right? All of you see it, or right? So then we find easily that the vector current is just V mu. The vector current will be, okay, there are two contributions, right? Because one contribution is when I take into account the variation of Q, and the other one is when I take the contribution of the variation of Q bar, okay? Let's pay attention to the first one. If we pay attention to the first one, so what we have is Q bar I, because then we have Q bar I gamma mu, right? I have just taken the derivative with respect d mu Qy, right? And now I have to put this delta phi, this total variation of the field, right? And this total variation of the field, is just T A Y Z Q Z. And then it will appear, well, the eyes, okay, so the eyes, the imaginary, well, there is here an eye, right? That I will, well, it's the covariant derivative, it's fine, it's correct. It's correct. Okay, and then I will have another contribution when I take the derivative with respect d mu q bar, and it's identical. So then we have obtained the vector current. Any doubt about that? Is it conserved? In principle, Netter's theorem is telling us that it's conserved, right? So let us check if it's conserved. So d mu v mu. If I compute d mu v mu, I am going to have two contributions, no? Because the derivative can add or either on q bar or either on q, right? So what I have is d mu v mu is going to be d mu q bar y gamma mu t a y z q z plus q bar y gamma mu, no, yeah, gamma mu t a y z d mu q z. Does it make sense to you? What can I do now? we make use of the equation of motions. If we make use of the equation of motions, thank you, Daniel. The equation of motion, okay, what appears in the equation of motion is the covariant derivative, right? So it's not true that E gamma mu d mu is just the mass. So it's not true that E gamma mu d mu acting on Q is just the mass times the field, because in the covariant derivative you have gluons, right? So then this thing is going to involve the mass plus gluons, okay? But you see that the mass has already appeared, okay? So just I have the nodes, then we get I N Y Q Y alpha minus G V mu A lambda A alpha beta Q bar Y beta gamma mu. Then we have here TA. We have this bit TA Y set. Then we have Q set alpha plus. Okay, this is what I was telling you, right? So it appears the mass, but we have some gluon stuff. These are also Gell-Mann matrices, right? But these Gell-Mann matrices are in the color space. Okay, so here probably you have Gell-Mann matrices as well, but these are in the flavor space, while these are in the color space. And now you're going to have a new contribution that comes from well, I think this contribution that I have written here, for sure, I should have a slash. This is the one that comes from here, okay? That I have obtained just taking the Hermitian conjugate of this and multiply by gamma 0, right? And now you're going to have another one coming from this derivative, okay? And this another one is going to be plus Q bar Y alpha T Y T A Y Z minus I and Z Q alpha Z minus G V mu A lambda alpha beta 2 then I have gamma mu and Q Z beta. I guess that should be something like that. Okay, so then we have, because now we are taking the derivatives of the field with flavor set, then it gets down the mass of flavor set, okay? So then in principle, you can check that the gluon pair cancels. The gluon pair cancels, and then you have that this is just I ny minus nz q bar y ta y z q z. Right? So the only thing that is left is this term minus this term. And the minus sign comes from, okay, perhaps it's a good idea, right? So if you have, okay, if the equation of motion is E gamma mu d mu minus ma qa equals 0, then what you have is q dagger. So you have qa, you dagger this thing, you will get minus I, then you will get gamma 0, gamma mu, gamma 0, d mu minus ma equals 0, right? I have done anything wrong? No, because I have just made use that gamma mu daga is gamma naught, gamma mu, gamma naught, right? Good. Now in this term, I can put gamma 0 free, right? By free, because gamma 0 squared is 1, right? And therefore, the equation of motion should be, if I am not doing anything wrong, it's going to be now q bar, no, because qa daga gamma naught is qr, so then it's going to be q bar. Now you are going to have gamma mu minus I gamma mu d, then we have minus na, and we have gamma naught equal 0, right? So then in principle what you have is this is equal to 0. So it changes. There is a minus sign difference, right? Okay? Okay, so it's conserved. When it's conserved? When the masses of all the quarks are equal. If they are, even if they are not 0, but if they are equal, then the current is conserved. In the case that you do for the axial, what happens is that you have an extra gamma 5. Sorry, there is any problem? This one. Yeah, this, well, I have one gamma 0 at the end. I can multiply here by gamma 0. And then if I multiply by gamma 0, then it disappears, right? Okay, but gamma 0 is not singular matrix, so the another matrix should be 0. Okay, what I was saying, yeah, in the case of the axial, what happens? That you have a gamma 5. And then when you have a gamma 5 and you do all of this business, there is one moment where you have an extra commutation with the gamma 5. And because this extra commutation with the gamma 5, what happens is that instead of getting here the difference of the masses, you get the sum of the masses. So therefore, to obtain that the axial current is conserved, you need that all the masses should be 0. Okay? By the way, there is something that is called partial conservation of the axial current. Partial conservation of the axial current is, okay, people work with axial currents just knowing that are not totally conserved, but the divergence of the axial current is small because it's proportional to the quark masses, right? Which for the U, D, and even for the strange is small. So this, you just see sometimes partial conservation of the axial current, PCAC. Okay, so next thing, commutation relations, which are essential. You remember I construct the theory of pions just assuming that this is correct, right? So how do we do this thing? Okay. Okay, so to do this, you need to quantify your theory, okay? Because you need to put into the game that the fermion fields, they don't commute, right? And then they follow some anti-commutation relations, right? So the key ingredient, here I have the notes that I have prepared for you, because this is a bit, well, it's 1 page, okay? It's 1 page. is one page. Let me just put some order into this. Okay, so now I should take into account the following. Right? Where is not a commutator. This is an anti-commutator, right? This is an anti-commutator. Everybody is happy with this, right? So you know that in the way that we quantize, we go to a quantum theory. Is you have a classical theory, then you say, in principle, the commutator of Q dot, the corresponding momentum is E h bar or whatever it is, right? But here, because we have fermions, instead of commutator, we have an anti-commutator. This is the Fermi statistics theorem. Okay, then, and then the important thing is that it holds at equal times. Tell me, at equal times. This is the origin of this delta. It's only equal times. Okay, so I am going to look at this. Pardon, sorry. Okay, I am going to take the commutator of two vector currents. And then I am going to take the, well, in principle, you know, that forget, I mean, so that will allow us to understand the first. QA, QB is I times FABC, QC times. And FABC are the only difference between Q and V. What is the difference between Q and V? That you have to integrate over the space, right? That you have to integrate over the space. Okay. So commutator. So this thing is going to be Q bar Y alpha X. I am going to put explicitly the Dirac indices, right? This A and B are different because here, mu and 0, yes. Yeah, because I have, in the notes I have mu and 0. Then if I put mu and nu, then at some point I will make a mistake. But it's pretty much the same, right? But look at, the 0 is really what you need because the charge is the time component of the vector current after integrating over space, right? So the 0 is what you really need, right? Okay, so I am writing this. Q bar, okay, this is index I prime. No, this is index Y, sorry, Y. So then I have gamma mu, AB, TA, Y set. TB set prime. No. Sorry. It's Q bar Y A gamma mu A B T A Y Z. Sorry, Y Z. And now we have Q Z alpha X index B Q dagger Y prime alpha prime position Y index C, and then we have TV Y prime Z prime Q Z prime. I have alpha prime, then I have here Y in the C minus Q dagger Y prime alpha prime Y Z TV Y prime Z prime Q Z prime alpha prime Y C Q bar Y alpha X A gamma mu A B T A Y Z Q Z alpha X B delta X0 minus B0. Okay, I think I have, okay, we have it here. And the only thing is I have put many indices, right? For once. So the vector current is Q bar gamma mu T Q. So it's Q bar gamma mu T Q. Everybody happy? And then I have put the Dirac indices in here in the game. So it's A, B, then I have B. And then, okay, can anyone tell me why it appears here Q dagger? And no Q bar. So now I am writing, and that's the reason why they have B0, just to make easier, right? Because there are two gamma zeros, right? Because in principle, you will write something like Q bar, no? Because if you look at the vector current, it's Q bar, but because it's the zero component, then you will have a gamma zero, and then Q bar gamma zero gives you directly Q dagger. Okay, and now you have to be a bit careful because you need to use, when you are with many indices and you have dummy indices, you should use different names. Otherwise, it's a nightmare, right? So for the second product, I have put primes, right? So it's Y prime, Z prime, so it's B. And then I have put the positions, X, Y, and so on and so forth. And in principle, here is in the other way around. Happy? Now, what we are going to do? I am going to make use of, I am going to change the order, right? Correct? And I am going to make use of this relation, okay? Here, I and J are all possible indices, color indices, flavor indices, Dirac indices, all of them, right? That's the reason why here, in the blackboard, I have put for once all possible indices, right? So let's see. This thing is equal to. Okay, so let's see if we just keep track of what is going on. So, okay, we have this delta x0, y0, right? And now we have, okay, we have q bar yx a. Now we have gamma mu a b. We have t a. One thing, when you are because I am putting explicitly the indices, then I don't care if I don't put in the right order, right? Because with the indices you know how to do all the multiplications, right? Nevertheless, I think that I try to be careful. So TAY Z, and now here I made use of the anti-commutation relation, right? So I am going to write this, correct? Okay, so this is going to be delta alpha alpha prima. Okay, is going to be delta alpha alpha prima. Delta BC. What else? Delta Z Y prime. Correct? And now this is going to be delta 3x minus y. Y delta 3, because I have already a delta x0 minus y0, right? Let me check that I haven't made any mistake. And minus, then I change the order, right? Minus q daga alpha prime y prime y index c q z alpha x index b, right? Is correct? Okay, so we close here the bracket, and this is multiplied by tb y prime z prime q z prime alpha prime y index c. Okay, so we have the first term. Add to any mistake that I may have done. Okay, so next, I am going to, for the second contribution, I am going to do the same business, but down here. Okay? Then perhaps what I should do is, okay, say that this is, because this is not Q daga, it's Q bar. Okay, so that should be something like Q daga Y, and then Q daga Y of index A, no, of index A prime, gamma 0 A prime A, and now here we have gamma mu AB, right? This is what we had, correct? I need Q daga. I cannot make use of the anti-commutation relation with Q bar, okay? So now we come back to the blackboard, and then we will have two mistakes. This minus sign, minus. And now Q daga Y prime alpha prime Y C TB Y prime Z prime. And now bracket. And we say delta alpha prime alpha. Delta C A prime. Delta Z prime Y, no? Y. And now delta 3x minus y. Okay? And then minus q daga y alpha x a prime q alpha prime z prime y index c. I close the bracket and I put the rest, which is gamma 0 a prime a gamma mu AB T A Y Z Q Z alpha X B. And I have the delta in here, right? Well, hopefully I haven't made any mistake, but I mean, the important thing is just to you understand what I am doing, okay? Good. So let us pay attention to the SS term, to the SS terms, which are those, okay? Okay, so if we pay attention to these terms, what do we have? I am going to copy. So we are going to have, so I am paying attention to the terms which have the delta 3, okay? If I pay attention to these terms, what I have in my notes is Q bar Y alpha X A gamma mu A B T A Y Z T B Z Z prime Q Z prime alpha Y B minus Q daga Y prime alpha Y C TB Y prime Z prime gamma naught C A gamma mu A B T A Z prime Z Q Z alpha X B. And this is Q bar Y gamma mu Q Z prime T A Y Z TB Z Z prime minus Q bar Y prime alpha no gamma mu Q Z TB Y prime Z prime TA Z prime Z. And this is Q bar Y gamma mu Q Z TA TB matrix element Y Z. Let us see if this is correct. Okay, so I have two contributions, this and this. Okay? The one in the first row and the one in the third row that it has a minus sign. And this is this minus sign, right? So what do we have here? We have Q bar Y multiplied by the matrix gamma mu. Then we have TAYZ, and then we have a lot of deltas that affect this. So now we have TB Y prime should be set, right? So that's the reason why we have Y prime, this is Y prime. So that's the reason why we have TB. Yeah, here. Yeah, we have, okay. No, here, sorry, I am looking here and it's wrong. We have TB Z prime, and then we have Q Z prime, alpha prime is alpha, and then B should be C, correct? And I don't care about X and Y because everything is multiplied by the delta 3, okay? The second term has the minus sign, and then what do you have? For the second term, you have Q dagger Y prime. Okay, alpha prime is alpha. All the color indices are equal. Then you have Y, C, T, B, Y prime, Z prime. Great. And now we come here and then in here we have sorry, I haven't written it. It's the second one. I write this, and now I have this gamma 0 of, I had A prime, but A prime, I had the delta AC. I have the delta AC. And then you have gamma mu AB, and then you have TA of Y Z, but Y now is zeta prime. Okay? And now we have QZ alpha X. Okay? So it makes sense. A, B, B. So this is just Q bar gamma mu Q in the Dirac space. And then you have Y, Y, Z, Z, Z prime, Z prime. So then you have this multiplication, right? While here, what you have is Q dagger and here CA, Q dagger, so Q dagger, I have gamma not CA, so then I recover here, I recover Q bar. Okay, because I have Q dagger gamma naught. So I have Q bar. I have gamma mu AB, so everything works. So then I have TB Y prime Z, and I have TA Z prime Z. And I have done it. Because what is the commutator of TA and TB? IFABC FC. Okay? Fine? I think that it doesn't pay off to, to continue, but I promise you that, okay, we have paid attention only to these two contributions. These and these contributions, they cancel, exactly. Okay? You can check that the other two, they cancel. They have opposite signs and they cancel. Okay? So then automatically what we have shown, so this contribution here, the one that comes from here, it cancels exactly with the one that comes from here. So what we have shown is that this is A, F, A, B, C, V mu, because this is V mu, right? This is V mu, correct? V mu X delta 4X minus Y. That's what we have shown. Okay? Okay, it's a bit tedious, right? But I mean, those who are interested, I think that it pays off to do just once, right? Then automatically we have already that QA, QB in the slide is going to be IFBC, QC. The only thing that we have to do now is to look at the zero component and do the integration over space, which is trivial because we have a delta function. Does it make sense to all of you? The rest of commutation relations are done in the same manner. Okay, so you see that these relations, they come directly from QCD. And then I repeat myself, but just if you get the flavor of the idea, it's very important. In nature, we don't have quarks. Well, sorry, In nature we have quarks, but we don't see quarks, right? So we see hadrons. So we need to do a theory with with quarks degrees of freedom. We need a theory with hadron degrees of freedom. Okay, so what we can do is to plug in a Lagrangian with all the symmetries. So Hermitian, CPT, whatever you want, and then to incorporate as many symmetries, approximate symmetries of QCD as possible. Here I have focused on on chiral symmetry, but for instance, in the heavy quark sector that Fenkun addressed, you want to write something consistent with heavy quark spin flavor symmetry, if possible. There will be unknown constants in the effective, you pay always a price. There will be unknown constants and you just fit the constants to experiment, okay? We have 6 minutes. Let me go to the Goldstone theorem, okay? I think it's important just to discuss the Goldstone theorem once in life. Okay, so the first thing I need is to have the proper nodes. Okay, so the thing is that we have a charge. We have a charge that does not annihilate the vacuum. Okay? We have a charge that does not annihilate the vacuum. So then I consider I consider the commutator of this charge with all the fields of my theory, right? These phi I are all the fields of my theory. And then this commutator is going to be, well, some constants. I don't know what the hell is, yeah, it's because I charge. This A is because I charge. So, right? So this commutator is going to be, I should be able to write this commutator in terms of the fields of my theory. Okay, this is what I have done it, right? Okay, if you say that QA doesn't annihilate the vacuum, then automatically what happens is that one of the fields of the theory takes a non-zero expectation value. Okay? I mean, you just, and let's suppose that is the field J, and then just for the sake of brevity, from now on, I am going to assume that okay, I am going to drop this J index, right? And in the slides, this is what is called operator O. Okay? Good. No, go ahead. No, here is not flavored. This is in general. I am just trying to prove the theorem in general. I said I have a theory where I have a number of fields, phi 1 to whatever is my theory, right? And then the only thing I am saying, okay, I pay attention to the commutation of the fields with this charge that doesn't annihilate the vacuum. This commutator should be written in terms of the field of my theory, and the fact that the charge does not annihilate the vacuum means that one of the fields should take a non-zero expectation value in the vacuum. Because if all the fields will take a zero expectation value in the vacuum, then necessarily the charge will annihilate the vacuum. That's the point. And what I say is, okay, let me call it 5. Just, I said 5J, but just for the sake of brevity, let me call it 5. Okay. Because I have invariance under spatial and time translations, right? So, so this phi x thing the field in the point in the space-time point x is e to the I px, the field at 0, e to the I minus px, okay? And because the momentum annihilates the vacuum, there is nothing with the translations, then this statement is equivalent. This statement is equivalent to say that this matrix element is not 0, right? Okay, because the only thing is this adds on the vacuum, this adds on the vacuum, and you get 1, right? No problem. Okay. So now I can compute this quantity. I can compute this quantity, the commutator of Q with this field. The key point is, does this quantity depend on time? Does this quantity depend on time? The answer is no. Why? Because, okay, I have removed all time dependence in here, and Q is a conserved charge. So we are just paying attention to, we have a symmetry, so we have a conserved current, we have a conserved charge, and it turns out that this conserved, this charge does not annihilate the vacuum. So this quantity doesn't depend on time. Let me call it this quantity C, and we know that this quantity is not 0, and is independent of time. Okay? Correct? Now we are almost done. I am going to insert a complete set of states. So this quantity psi is going to be the sum over n of vacuum q n n phi 0 vacuum minus vacuum phi 0 n n q vacuum. I have done nothing, okay? Now I remember okay. Now I remember that Q is D3x J0 xt, right? So therefore, what I have is that psi is the sum over n, the integration d3x, then we have vacuum, and I have in here IPX, IPX J0, 0, e to the minus IPX, then 0, no, sorry, then N, phi 0, 0, minus vacuum phi in 0, N I to the IPX J0 in 0, e to the minus IPX vacuum. The only thing I have done is to take into account that this is J0 of xt. I have made use of invariant and the spatial and time translations, okay? Good. This is one. However, this is no En. Is the full momentum. Is the full momentum, right? So there is still one. There is still. So then this thing is going to be sum over n d3x. Then we are going to have vacuum j0 in 0. Then we are going to have e to the I minus pnx, right? Then n. Then we have n phi 0, 0 minus vacuum phi, the field in 0, n I to the IPN x j0 in 0 vacuum. Okay. Good. Can I do the integration over x? Can I do this integration? Which is the unique dependence in x there? In the exponential. So this e to the, so this e to the minus IPN x that I have here is e to the minus IN energy time e to the plus IPN x, right? So then I can do the integration over x. That is going to give me a delta, a three-dimensional delta, right? So we are almost done. So therefore, I conclude that C is 2 pi q sum over n delta 3 of Pn e to the minus ENT vacuum, the current at 0 and okay. So what's the problem now? That I started with something that it was independent of time. And however, in the right-hand side, you have an explicit dependence on time, right? So the right-hand side depends explicitly on time. At least what? At least what? Here I am summing overall hadrons. So then if all the hadrons which are massive, they don't have overlap with these operators, right? Then the contribution of the massive hadrons will vanish. Okay? But we now, yeah, so there are two important things. Is that C doesn't depend on time, but I know that C is different from zero. Right? So if all, so look at the point. If the overlap of the operators with, so if I want C equals different from zero, and the overlap of my field with a massive operator is not zero, then automatically I have a dependence on time that I don't want. Okay, so necessarily there exists one state such that correct? But the mass of this state should be zero. It should be a massless particle, right? Because otherwise, so I need an state giving some contribution to psi because I know that psi is different from zero, correct? But at the same time, the state that is giving me this contribution different from zero should be a massless particle. And this is Goldstone theorem. Okay? This is Goldstone theorem. If you break a charge, then automatically in your theory there will appear a massless particle, which is called Goldstone. And you see that this has been deduced just from first principle. I haven't used, the only thing I have made use is invariant and the translations, space and time translations, right? Okay, I think that we should stop a little bit. And now I am not going to say anything else about QCD, okay? So if you have any doubt, you just say now or forget. Okay, so shall we resume in 10 minutes? Good. I want to tell you things about the lambda 1405, okay? I want to tell you things about the lambda 1405. And then there is one thing which is very important. You should get used to the PDG, right? The PDG live, and they are in the web. You can find details of any particle, right? So I think that yesterday we already spoke something about the lambda 1405. Okay? The lambda means that the isospin is zero. Also, lambda means that there is a strange quark. Okay? So then the quark content of this hyperon, of this baryon, should be just S d u. S d u. But the d quark and the u quark are coupled to isospin zero. Okay? And I think that yesterday we discussed that therefore the spin should be also coupled to zero. The spins, yeah, the spins of the d and u core are coupled to zero, and then okay, there is something very important that I have not told you, is that the spin parity of this hyperon is 1/2 minus. Okay. Why I think it's interesting? Why I think it could be called exotic, right? Uh, in principle, there is nothing that could be bring your attention just immediately to say that it's exotic. No, it's not. I think that Fenkun mentioned in his last, well, yesterday, pentaquarks, right? Pentaquarks just are exotic because you have CC bar, and then you have you have three lights. Okay, so then automatically the pentaquarks that Fenkun was talking about, they are immediately are exotic because they have hidden charm. So then because they have hidden charm, automatically are exotic because corresponds to a structure of 4 quarks and antiquark. It's not the normal structure of 3 quarks in the case of baryon, or QQ bar or quark antiquark in the case of mesons. Okay. In principle, there is no problem. I mean, people working in constituent quark models, they have some potentials for the quarks. There is nothing new, right? Typically, the potential between quarks typically is just one gluon exchange. They put by hand confinement, and they have some phenomenological parameters, the mass of the quarks in the concentric quark models, which are not 5, 10 MeVs, typically out of the order of 300, no? Because if you do a constituent quark model, you want to describe the proton, then you have 3 quarks of 300, and then automatically you have 900, okay? But then the people, the colleagues working in constituent quark models, they have quark potentials, which have been fitted to some phenomenology, and then they can take these potentials and they can solve. It's not a Schrodinger equation because it's a 3-body problem, right? They solve the corresponding equation and then find, okay, with these quantum numbers, and then okay, they will find. So they just look at. If they just look at the spin and isospin, then they will find the ground state, that is 1/2 plus. And also I think that we just mentioned, it was 1/115 or 1/116, depends. MeV, okay? And then they just find excitations with a spin parity 1/2 minus that could correspond to the lambda 1405. Okay, there is nothing. The only thing is that to accommodate the parity, you need to include 1 unit of angular momentum, orbital angular momentum, because otherwise you cannot get the proper parity. And that's the reason why these baryons are called P-wave baryons, right? The ground state, it will be an S-wave baryon, right? 1/2 plus, everything is in S-wave. So you have S, you have U, you have D, you have S, everything is in S-wave. You have 1/2 plus. Yes, tell me. Well, it corresponds to the excitation. So I mean, when you just solve a Schrodinger equation, then there are some excitations, right? So it depends to the excitation energy. And of course, I mean, if you inject angular momentum, so the energy is larger. Okay. So gluon exchange incorporates spin-spin interactions, incorporates spin-orbit interactions, and so on. It's complex, okay? The only thing is that the ground state, everything is in S-wave. Well, the largest component of the wave function is everything in S-wave, right? But in physics, if something could happen, it happens, right? So there are also some contributions. No, this is very important, right? So you need some good argument, and a good idea to prevent something to happen. A good idea and good argument is asymmetry, right? So for sure, in the final configuration, in the real configuration of the ground state will be also D wave components, right? But the importance is much smaller. Okay. What's the trouble with this? That the people, the colleagues working in constitutive quark model, they can describe very well the ground state baryons. So lambda, nucleus. You remember that I should have here. Yeah, here. No, sorry, here. They describe very well the ground state baryons. They describe the sigmas, the lambdas, the nucleon, the proton, and they take this potential where they have determined all the parameters, they compute, and they fail around 5 by 100 MeV to reproduce the mass of the lambda 1405. Okay, so typically normal calculations in constitutional quark models, they get that the excitation is of the order of 500 MeV. Okay, so then we have a trouble. Okay. You know what a resonance is? I think that Fenkung has mentioned this morning about resonances. Actually, the lambda 1405 is a resonance. It's a resonance in the sense, okay, that's important. Is the ground state of the lambda 1/2 plus a resonance or not? Why? Because it cannot decay through a strong interaction. It's not stable. The ground state is not stable because it has a weak decay. Okay, so the lambda can decay, for instance, into a proton, a pi minus. But this is the dynamics of this decay cannot be strong. Why cannot be strong? Because I am changing flavor. Because the flavor quantum number, the strange flavor quantum number is not being conserved. I had one unit in the lambda and I don't have in the final state. Okay, and you remember when we construct the QCD Lagrangian, we found that the flavor quantum numbers were conserved. You remember? So this cannot be a strength. So this is a weak decay. Okay, so it has a width. Okay, but the width has Fenkun talk about Bigner and things like that, distributions? Okay, look, perhaps we should stop the recording. I am not sure if I want this thing to, but I am going to tell you to be reproducible, right? Okay, you know that the time dependence is something like that, right? Okay, so if the particle is not stable, if the particle is not stable, what happens is that the energy becomes complex in principle. And why the energy becomes complex? Can anyone just to tell me why the energy becomes complex? Because it can disappear. because there are some channels that I am not considering in my, okay, if I solve, if I am solving and I am not taking into account this channel proton pi, right? So there are channels that disappear. And actually, what happens here is e to the minus I e to the minus gamma t. You see? So then it decays. That also means that the energy of this system is not well defined. It follows a distribution. And this distribution is, well, it's not the Breit-Wigner. One easy way to model the Breit-Wigner, sorry, one easy way to model this distribution, but sometimes it's inexact, it's not correct, is by a Breit-Wigner. In the same manner that I will always tell that I have never told you this thing, right? And you know that the Breit-Wigner, what happens is, okay, this is a distribution of this type. E is, the energy is something like that. Okay, so it's peak around some value ER, so that will be ER, okay, but it has some width, right? It's a Lorentzian thing, right? It's a Lorentzian thing, okay, and that has to be with the width, okay. So then that means if you measure many times the energy, the mass of the particle, then you get different values according to this distribution, okay? We call resonances those particles who can experiment, those particles which can decay through a strong process, through strong reactions, right? Those particles which can decay through a strong reaction. And why this is happening? This is called resonance, because if the decay is strong, the lifetime is very, very small, and the width, and the typical width of these particles is 1 mega electron volt. Is the typical width, is the unit, no one. I mean, MEVs. It could be hundreds of MEVs, tens of MEVs, right? That means, if I remember correctly, I think that a width of 1 MEV, I think it's 10 to the minus 24 seconds or something like that, right? It's 10 to the minus 24 seconds, and then we call it resonance. So you cannot, you only produce resonances really in scattering experiments, right? Because you cannot, with these small lifetimes, right? You cannot have a bin of resonances, right? Because they will disappear. You only produce resonances in scattering problems, right? So for instance, you do the easiest thing, A plus B going to A plus B. You just look at the face, you just look at the cross section, and then there is some particular energy, so the cross section does whatever should do, but there is one particular value of the energy, of the center of mass energy, where you have an increase, a peak, a maximum, and then you identify this thing with a resonance, okay? This is one way to see it. Because if the decay is weak, the lifetimes are the order of 10 to the minus 6, 10 to the minus 8. For instance, the muon decays through a weak process, and the lifetime is, or the neutron. What is the lifetime of a neutron? Okay, so, but why? Because it decays through the weak process, right? Neutron going to proton, electron, and antineutrino, electrónico. Okay? So the thing is, okay, the core model people, they file really to understand the lambda 1405. So then, in principle, suppose that I look at to nk bar. Sorry, nk bar, nk bar. to this reaction. Suppose that I look at to NK bar, to this reaction. And suppose that I pay attention to S-wave. So the nucleon, N is nucleon. The nucleon and the antichaon are in S-wave. And then what is the spin? So then what I have is, I mean, diagrammatically, I may think in something like that. I have here my nucleon, I have here my antichaon, then maybe produce something. I may think about something like that. So which are the quantum numbers of this intermediate state if they are in S-wave? One half plus, this is a Goldstone boson, 0 minus, and the iron in S-wave. This object has, what is the spin parity of this object? 1/2 minus, right? Oh my God. Is the spin parity of the lambda 1405. What about isospin? Can I couple a nucleon and antichaon to isospin 0? Yes, yes. What is the isospin of a nucleon? If you want to do hadron physics, you need to know the quantum numbers. What is the isospin of the nucleon? 1/2. What is the isospin of antichaon? Well, antichaon. I told you yesterday. Antichaon means strange and a light guy. So what is the isospin of antichaon, of an antichaon? 1/2. If I have NK bar, I can couple to what? 0, 1, in particular to 0. In particular to 0. And the parity is minus. In principle, it may happen that if I look at to the cross section of NK bar going to NK bar, I may see something, right? For instance, there is one resonance which is very, 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 very famous, which is the delta. The delta, right? If you look at the cross section, of P plus proton going to P plus proton, then you have something like that. And this is 132, and this is, I think that the width is 180 MeV or something like that. I don't remember exactly this number. But this is the famous delta plus plus, the delta 232. Okay? This is the delta 232. Okay, so it's an enhancement in the cross section. Okay. There is a trouble. What is the mass of the NK bar pair? The mass of the nucleon is 950. The mass of the kaon is, 490. Okay, you are more precise. So you sum, this is 3, and this, it cannot be a resonance. The lambda 1405 cannot. The lambda 1405 cannot be a resonance, no? Because for the lambda 1405 is below threshold. Is below threshold. So the threshold here for this reaction is 130. And the energy and the mass of the lambda 1405 is somehow here. Okay? But perhaps could be what? If it's not a resonance, it could be what? A bound state of NK bar. No? Because Fenkun has told you that if you have some structures below threshold, these are bound states. If the structures are above thresholds, you should call it resonances, okay? But, okay, the life is a little bit more complicated, because why only NK bar? Could I have pi sigma going to pi sigma? Sigma, spin parity, 1/2 plus, because belongs to the same octet as the nucleon, right? 1/2 plus. The spin parity of the pion, 0 minus. So then again is 1/2 minus. Quark content is exactly the same. The only difference is the sigma has isospin 1, right? Sigma has isospin 1, but the pion has isospin 1. If I couple 1 and 1, can I get 0? Yes. Yeah? Yes. What about the thresholds? What is the mass of the pion? 140. And the mass of the sigma? Something like that? Works for you? Oh! 1,325. Okay, 1,325. So in principle, the lambda 1405 could be a resonance of pi sigma. But life is a little bit more complicated because you have to, well, because what I have written until now are elastic processes. K bar, anti-kaon nucleon going to anti-kaon nucleon, and I have written anti-kaon nucleon going to pi sigma. Okay, but you have to consider also some inelastic channels. That could happen. Why not? I am violating any quantum number. I can have k bar n going to pi sigma, and then pi sigma going to k bar n, and so on and so forth. And I have more channels. What do you tell me about lambda eta? What is the spin parity of the eta meson? The same as the spin parity of the pion, is in the same octet. So then again, lambda eta is, in S wave, is 1/2 minus. And what about isospin? The isospin of the eta is 0. So it's perfect, isospin 0. I could also have also this, kaon cascade. Kaon is not the same thing as anti-kaon. Kaon is the antiparticle of the anti-kaon. And then kaon means anti-strange. Okay? So kaon has an S bar. An S bar, and we have a light guy. But cascade, what does it mean, cascade? Too strange. Okay? So then I have an anti-strange, I have a light guy, and here I have two strange, and I have also another light. So what is the quantum number content? Strangeness minus 1, perfect. So strangeness minus 1, it means one strange quark. And what about spin, parity, and isospin? It works. Because the kaon is in the same octet as the pion and the anti-kaon. So it's spin parity 0 minus, and the cascade is in the same octet of the nucleon. So it's spin parity 1/2 plus. 0 minus and 1/2 plus, 1/2 minus. And what about isospin? You see, isospin you have 1/2 coupled to 1/2, 0 and 1. So then, in principle, what I am going to show you is, okay, I am going to take into account coupled channel dynamics. I am going to take into account, I am going to study reactions involving coupled channel dynamics of these 4 final states. Okay? But, okay, Fenkun maybe mentioned bound states, mentioned resonances. I think that he showed you a lot of exotic states, but have you wondered how do you get something like a bound state or something with some structure? Can you get this thing in perturbation theory? In your quantum mechanics courses, how do you get bound states? Sorry? Solving the Schrödinger equation, right? And the Schrödinger equation is something that is non-perturbative. So, okay. So you have a potential, right? You have a potential, right? How I write it? Okay, you have a potential, and then if you just suppose that you have a potential, this is the potential, right? Then you need to find a bound state, you need to do a non-perturbative resummation. And you need to solve the Schrödinger equation that it puts you many insertions of this potential, right? It does for you the ladder sum, right? Okay, you need to resolve this thing, right? So you need to invert this operator, okay? Or you need to solve the Riemann-Schwinger equation. I think that all of you are used to the Schrödinger equation, but I don't know how many of you have ever heard about Riemann-Schwinger equation. They are totally equivalent. The Riemann-Schwinger equation tells you that the scattering matrix, which is just the resolvent of this operator, is just something like that. Sorry. V plus GT. Okay? This is the Riemann-Schwinger equation. So, okay, so I am sure that you have done some time, right? So then you may say, if I do perturbation theory, you say a first order T is V. A first order T is V, right? Then I can go to the next order and I say, okay, the next order T is V plus V, G, and instead of T, I put V. Okay? Then I can go another order in perturbation theory, and because you see the problem is that T is here, right? So then you say is V plus V, G, and instead of T, I put order 2. V plus V, G, V plus. No, order 3 is here. But I can continue, right? And then if I don't this thing diagrammatically, what I have is, okay, so these are going to be my baryons, and these are going to be my mesons, and this is going to be my potential. And my potential is going to be S wave, Wigner-Eckart. No, Wigner-Eckart. Weinberg-Tomosawa. You remember that yesterday we spent some time talking about Weinberg-Tomosawa. So that will be T equals V. Diagrammatically, that one will be what? Let's see, something like that. No? 2 insertions of V. And by the way, I haven't mentioned it, right? But this is, what is this? This is the green function, the propagator G, okay? That in quantum mechanics is something like that, no? But I will be using quantum field theory and it will be my loop function. The third order will be what? Just help me. Will be what? Please, help. What they do? Pion, so meson, then I have a baryon, and now what they do? V. So now I am just trying to get this contribution, right? Because at third order, I have B, which is the first diagram. I have BGV, which is the second diagram. And then I want BGVGV, right? Help me. What they do? 2 loops. Thank you. Right? Actually, oh, it's true. I mean, formally, it's not correct that T is 1 minus Vg. Right or not? From this equation here. Let's see. This is T, 1 minus Vg, V. So then T is V1 minus GV. And now you do an expansion in powers of Vg, and then you are getting all the series, no? I am doing the things in the simplest manner, in the sense that if V and G are matrices, in particular if V is a matrix, because we will have, because coupled channels, V is going to be a matrix, one has to be a bit more careful. One question. I haven't said anything, but you know what T is? When I mentioned Riemann-Sugar equation, everybody was happy with the Riemann-Sugar equation. So then I assumed that everyone knew what the Riemann-Sugar equation was. It's the scattering matrix operator. And can anyone tell me things about scattering matrix operator? The experimentalists, you should know a lot about the scattering matrix operators, right? Any volunteer? Anyone? But you know what this, you know or not? That's going to be a bit difficult, eh? But Fenkun was talking about Riemann seeds of this object, eh? Riemann seeds of T. And he was talking about poles, and he was talking about poles of the T matrix, right? So how was it? You have no? You have the scattering, for instance, the particle A, particle B, I am in the center of mass system. The initial momentum is P, and then I am going to do elastic. I have A, B, but in the final state, the center of mass momentum is P prime, and there is a basic object, which is the cross section. And omega is the I mean, you don't need to take notes. This is in any quantum mechanics book, right? And this is the solid angle distribution. So this turns to be this thing. And F is the scattering matrix, okay? That takes you from momentum in center of mass as P to momentum in center of mass P prime, right? So the T is an operator that provides you this, okay? Loosely speaking, it provides you this, okay? This object. And this is the quantity that our experimental colleagues, they measure. Okay, they have some bins of the particle. Well, maybe B is a target and A is a bin, or if they do in a center of mass, right? If they just collide proton-proton like in LHC and in LHC, and then in some direction they just count how many particles they see. And they divide it by how many particles they have sent, and this, well, you have to do a little bit more careful with this, but this is the idea, okay? So this T is an object, this T is an object that determines this amplitude, this scattering amplitude, okay? Good. So Fenkun has told you that poles of this scattering of this amplitude are related with bound states, are related with resonances. And actually, when you go to the complex plane, the poles cannot be in any arbitrary position, because then you break something called causality, right? But this is something that somehow you knew. Somehow you knew. You remember your when you study, yeah, when you study quantum mechanics, right? When you study quantum mechanics and then you have a square well, right? You have a square well of depth minus V0 and then with some width R, you found bound states, right? You remember that you found bound states. And I am quite sure that you also solve for positive energies, right? You also solve for positive energies. Bound states are for negative energies, and you also solve for positive energies. And then when you solve for positive energies, you were obtaining this, well, typically what happens is, because if you have symmetry under rotation, then you do a partial wave decomposition, and then typically you were, and this is what we are going to do. You were, for instance, in this case, well, you just compute one of these for a given angular momentum, right? And I am quite sure that maybe your teacher told you that the poles, and you can check it in your notes, look for the poles of the amplitudes that you found in the scattering, and you will see that these poles are precisely the bound states. Okay, so then the concept that Fenkun was telling you is something that you knew. But the poles, well, you have to go to imaginary P, right, to find the poles. Okay, so then, but you see, to find poles, you need to do something non-perturbative, because when you solve this quantum mechanics problem, you were doing something non-perturbative, because you were solving the Schrödinger equation. Of course, if you just do this, you don't find any pole, because either the pole is already in the potential or you don't find any pole. To find some extra pole, you need to do a non-perturbative resummation. And you can see here, because if I do a non-perturbative resummation that amounts to do all the sum, automatically, well, it may happen that B does not have poles. But where I can look for poles? In 1 minus VG. No, poles no. I can look for zeros of 1 minus VG that it will provide you poles. So the first measure, and I have to stop, the first measure is that you need to do a non-perturbative resummation to find poles. And to find any of the exotic states that Kuhn was showing you in the previous lectures, theoretically, we just find this because we just resum the Riemann-Schwinger equation, or sometimes we call beta-Salpeter equation if it's relativistic instead of non-relativistic. Okay? Just 5 minutes, and just more for 5 minutes more. Okay. Let's come back to this object. I don't know if you remember, but this object, so I am going to focus in S wave. Okay, this partial wave decomposition, okay, look, this thing depends on the energy, right? And it depends on the angle. And just because you have symmetry and the rotations, then you say, okay, all the angular dependence is just this Legendre polynomial, and then the amplitude depends only on the energy. You remember what a phase shift was? You remember phase shifts? Phase shifts were obtained from this. Just saying that your amplitude scattering, your scattering amplitude was e to the twice I delta minus 1 divided by 2 okay, K. K is, if it's not relativistic, it's 2 mu. This is the reduced mass. And this is the energy. And then it's, okay. In this context, it will be equal to the modulus of P and P prime. Okay, good. And this is actually what the experimentalists measure are phase shifts, because the cross sections, the differential cross sections provide phase shifts, full stop. This is the quantity that is observable. And this is just the relation. This is like the S matrix. I know that I'm telling you many things. And this is like the T matrix. This is the relation that there is between the S matrix and the T matrix. You have seen sometimes in some codes, something like that. And that depends on the convention. This is phase space, right? This is the relation that there is. In my convention, there is a 2ik. Okay? So I said just 5 minutes. Let me just rewrite this thing in a different manner. E to the I delta sine delta divided by k. It's the same thing. And let me just calculate f minus 1. F minus 1 is f complex conjugate divided by the modulus of f squared. This is true, eh? You just multiply, if you just multiply f by f minus 1, then you get 1. Okay, and f complex conjugate is e to the minus I delta sine of delta, and then you divide here by, you have k, and you have sine squared delta. No, yes, you have it. Okay? I am going to remove this. And with this, I finish. I am going to compute the imaginary part. The imaginary part of the inverse of the amplitude, the scattering amplitude, is minus k. Just compute the imaginary part of this. It's minus k. While the real part of the inverse of the amplitude, of the scattering amplitude is k cotangente cot of delta. So the important measure is, this is unitarity. So unitarity is fixed. This is related with the fact that the S matrix that's related with this, right? And then automatically, in the inverse amplitude scattering amplitude, the binary part is just kinematics, is minus the momentum, full stop. While the real part is complicated because, I mean, involve the phase shifts that involve the dynamics that you don't know what the dynamics is. And probably, and now I finish, you have heard about scattering length, effective range, etc. Is okay, we don't know what the hell k cotangente cot delta is, we are going to parameterize. This is going to be 1 minus a plus 1/2 R0 k squared plus dots. This is, well, this could be minus or plus, depends on the convention. This is the scattering length, and this is what is called effective range. And the only thing is that you can show that this is a function of k squared. And then effective range is that you stop after 2. Okay? The Riemann seeds that Fenkun was talking about is because this. Because the momentum. The momentum is a square root. So automatically, it's not, it has, the square root has Riemann seeds, right? It's not well defined. And probably he mentioned just 2, which are the 2 Riemann seeds of the square root. Okay, so we have learned, and then I stop, that the amplitude scattering is a multivalued function with 2 Riemann seeds, because you see clearly in the inverse of the scattering amplitude, and then that we don't know anything about the real part. The real part is something that you have to compute, and then is the most difficult part, because the imaginary part is trivial, it's minus k. The real part requires dynamics, and it's very complicated because you have to renormalize all the loops. And then the physics, many times, is just in the renormalization. When I do all of these diagrams, I get many infinites that I need to renormalize, and I need to define my renormalization scheme. This is not trivial at all. I need to get rid of the ultraviolet in a consistent manner of the ultraviolet divergences that you probably enjoyed quite often, right? I mean, just putting loops is not by free. It takes some. And I am sorry, just one thing. If you just stop your expansion here, only one order, perturbation theory, only one order, F is V, is real. You don't have unitarity. And when you do perturbation theory, and for instance, you consider, you are very strong, and you consider 1, 2, and 3. Okay, you have some imaginary parts which are consistent with elastic unitarity in perturbation theory, but is not exact unitarity. The inverse of the scattering amplitude is not minus k. Okay, so I need to do something to restore unitarity. So this is what I am going to do, and I am going to do in the courses of the lambda 1405 with these 4 channels that I told you about, using the interaction that we deduced yesterday. I look for poles, and we will find that that one of these poles can be identified with the lambda 1405. And it has a chiral origin, because why it has a chiral origin? Because I will be using my chiral interactions. Okay, sorry, I was late.